Okay, it's recorded right now. Okay, first announcement. We are going to have homework number 8 today, and then likely will be evening, like we used to have. Okay, it's going to be due on next Thursday. You guys know the drill, right? And then I'm going to put this assignment, and then you guys have to upload your file before 12:30, before class. Okay, I do see everyone upload their midterms quite successfully. I'm glad to see that. We do receive email from the school, want to know how you guys doing, which means that they want lecturers, instructors to see to re-emphasize to student whether or not you guys are doing well or any difficulties in terms of learning this class. So if I don't know if everyone is on right now, okay, about 31 students on right now. So if you do find any difficulties, I mean, I like person-in-person teaching. I really don't like this kind of remote teaching whatsoever. But if you do find any difficulties learning from remotely, and then you please don't hesitate to let me know. Okay, we'll do our best to help you to go through this process. Okay, so if not, let's go back to our class. So last time we talked about p-value, and later on we'll go back to p-value because you do receive email from me posting about the p-value statement from ASA. I want to go through a little bit and let you know that what's going on right now in terms of our society thinking about p-value. Okay, but before doing that, okay, I said last time I'm going to tell you about so-called union intersection test and the intersection union test. Okay, I said that this guy right here is really nothing but logic game. Okay, which basically means that if you are doing testing about A and B, okay, you have A hypothesis, you have B hypothesis. You have two hypotheses, or more than two. Of course, more than two is possible. And then especially nowadays, we talk about multiple testing a lot. Okay, say you have an A and B test. Okay, if you want to know that whether or not your both A and B are true, okay, both statements are true. Maybe your null hypothesis is both true. How to reject your null hypothesis? Really, only rejecting what? Either A or either B are wrong, right? So you do individual testing, okay? In order to reject the null hypothesis about both A and B are true, then as long as A or B are wrong, you reject it, okay? Likewise, if your null hypothesis actually A or B are true, okay? That means what? That means in order to reject the null hypothesis, you need to make sure that both A reject and B reject. Okay, this is so-called union intersection test or intersection union test. I always mix up these two guys, so I'm not going to go into detail about which one. Then look at the example, and you will know that which one is union intersection test, which one intersection union test. Okay, I guess the first one is actually union intersection test. You can see right here, null hypothesis is different testing intersect together. Okay, that means I think this guy is union intersection test, and this guy is intersection union test. Okay, good. Let's go to the example. You will see more clearly what I mean by intersection union or intersection test. Okay. So, say if x1 is no more theta 1. Okay. We are trying to testing whether or not null hypothesis theta is 1. and then alternative theta doesn't equals to 1. You guys might want to mute yourself. Okay, so I won't hear about background noise. Okay. Yeah, thanks. Okay, so easy this kind of simple hypothesis, we can actually try to divide hypothesis into 2 parts. Okay, one part is theta bigger than 1 or equal to, the other part is theta smaller than 1. Such that your null hypothesis would be what? Your null hypothesis theta equals to 1 would be your individual one A and individual one B, then intersect together. Then by intersection, theta is 1. Okay, so that means the original null hypothesis could be done as H0 and intersect with H0. Okay, then remember, going back to this, intersect means end to us in logic. End. Okay, that means in order to reject the null hypothesis, as long as you say A wrong or B wrong, exactly right here. Okay, that means based on the H0, you can construct it. The first rejection region is what? This H0 right here. Okay, then basically one-sided test. Then you're using one-sided hypothesis. You want one-sided critical region right here. As long as X is too small, I'm going to reject the theta bigger than 1, making sense. Likewise, your H0 is theta smaller or equal to 1. Okay, good. Then, yeah, I may be wrong right here. Okay, it's fine. So, okay, so H0 right here is theta smaller than 1. So in order to reject the H0, I have in that the second rejection region, X is bigger than B. Okay, that means as long as X is big, I reject the null hypothesis. Okay, again, it's because original null hypothesis is the intersection between H0 and H0. Then how I reject it? I reject it as long as either one is wrong or either 2 is wrong. That means it's actually union to us. Union is all to us. Either R1 or either R2. I reject the null hypothesis. Quite straightforward. That means eventually, if union pretty much the same thing as this is, I'm going to reject the null hypothesis. What? In terms of either X smaller A or X bigger than B. This is your new rejection region. It's actually matching with what we talk about it. I have single versus composite sided. I'm going to using what? 2 tails to reject it. My null hypothesis. Okay, good. That's so-called intersection union test. Then how about intersection union then? Okay, I'm sorry. That's so-called about union intersection test. How about intersection union then? That means this is all in null hypothesis, and then to reject that the null hypothesis in all A or B. Going back to this, right? To reject A or B, then we have to say both A and B are wrong. That's exactly what a rejection region is for intersection union test. Okay? Then your null hypothesis, or then by end, every statement got rejected to reject your null hypothesis union. Okay, this is quite good. This is quite good example in biostatistics because we see that all the time. By that means we are going to test a drug or testing a treatment, okay? And then of course we want the patient to be response to a treatment, okay? We want
hey Mike.
Okay. Then we want, again, you want to mute yourself. Okay. Okay, so let's go back to this. So of course, we want the patient to respond to treatment. Okay, so we are going to the treatment effect.
Yes. I'm looking at your code in some part I don't understand. Maybe I can ask you later.
Which part? Oops.
I can get your hierarchical lasso part and also group lasso part, but the
okay. Okay, I figure who's talking, so I will mute already. Okay, so let me see. Okay, so far so good. So when we do the trial, okay, we want the patient to respond. So we collect that there's a variable, okay, indicators to indicate whether or not the patient responds to treatment. But in the meantime, sometimes if you give like the drug dose is too much, then patient may have what? May have side effects. Okay, so that means when we do trial, we are not only collecting about the responses to treatment, but also collect that whether or not the patient have adverse events, of course, side effects. Okay, that means in order for the drug to work, we want both to happen, which means that they want them to respond to treatment as well as not having any side effects. Okay, that means in my logic is what? I want both hypotheses to hold simultaneously. Okay, so that means right here it's your null hypothesis actually either what's the proportion of how likely the patient response to treatment is 80% right here, or your side effect not going to be greater than 50%. That means as long as sorry about that. So this is A right here. This is hypothesis A, hypothesis B right here. Then in terms of O is basically the union. Okay, that means in order for drug to approve, we want to reject both RA and RB. Okay, we want them to both reject, so we can make sure that the drug not only could cure people, but also is safe for people to take. Okay, so that means you do need to working on the so-called intersection union test. Oh, sorry, intersection union test. Okay, so far so good. Any question on this? Okay, good. So let me make a final comment about why this is important right now to us. Okay, so really so-called multiple testing things. Okay, right here especially, I think it's quite important to the union intersection test right here. Let me see. Let me see which one should be more important to talk about in terms of multiple testing. Okay, so what I'm trying to talk about is this. So nowadays, especially, we are living in the era of genetics right now. A lot of times we need to show that your multiple genes or multiple synapses do have that association with any phenotype or genotype. So that means we usually facing one thing is called multiple testing. Multiple testing means that you do need to testing your hypothesis multiple times. I mean, multiple hypotheses. For example, you do have H1 or H01 or H02, then until H0M right here. Okay, so imagine this. Why do we usually do like so-called adjustments to testing it? For now, we sort of imagine you do testing, you will make error, right? Either type 1 error or type 2 error. I keep saying that it's frequentist approach, always protecting type 1 error, which means that also means that when you do a testing, you actually want to reject null hypothesis. What's the reason you do want to reject a null hypothesis? The reason is, if you reject a null hypothesis, the only thing will make error is type 1 error, which is only, for example, 5%. You do know it's a low percentage of probabilities if you reject the null hypothesis. Say if you do not reject, if you do not reject null hypothesis, what happens? You are going to make type 2 error, and then you don't know how much type 2 error you are making. So that means when you do hypothesis testing, you always want to reject the null hypothesis. So you would know that the largest error you would make no bigger than 5%. Okay, good. Say if we really naive to say it, if we actually reject null hypothesis, so we are going to make errors alpha 1 right here maybe. Oh, it's alpha. Okay. Okay. So naively speaking, it's we have a 1 alpha chance to make it right. Okay, good. So in terms of intersection union test, or by any means, it's if you want to have every hypothesis to be correct, and every hypothesis you have alpha chance make it wrong, 1 minus alpha chance to make it correct. Imagine if you want to have every hypothesis to do the right thing, which means that it's as long as you do one thing wrong, the whole thing is wrong. Making sense? Right? When you make a statement, you want to say, hey, A and B are correct, or A, B, C, and both are correct. Okay. But you do know, in order to reject this statement, A or B or C, one of them are incorrect, you mess up. Okay. If you do this many testing right here, say if each hypothesis have alpha probability, you make it wrong. Only 1 minus alpha probability make it correct. You want to make everything correct, basically, you imagine this, right? 1 minus alpha with power m. Okay? So imagine nowadays, m just goes to infinity. Oh, really large. Okay, you test in million, or not million, maybe thousands of genes simultaneously. And then what's the error you are going to make? Okay, right? The successful probability you make every statement is correct is 1 minus alpha with power m. When m goes to infinity, this guy right here goes to 0. That means whenever your number of testing growing, the chance of that you make every statement is almost 0. Okay? So if you choosing to using alpha for every testing. So nowadays, I don't know if our department do offer this kind of thing. I think so, because I think some of the classes is going to talk about this kind of testing it. Okay. Say if we do have every testing using the same alpha as type 1 error, then inevitably you are going to make error anyway if m goes to infinity. Then what should we do that? Okay. So nowadays, if you go to the seminars, okay, if you go to any lectures talking about multiple testing problem, one common thing people would do is what? It's actually not using alpha for everyone. Okay? So by mathematical, and I'm going to show you here, by mathematical, we know that right now it's, we could divide it by every alpha by n. Right here. Then I basically could control that the error probabilities or successful probability on the other side. We control the error probabilities. Let's do that. Also 1 minus alpha. Let me show you. This is error probabilities right here. Okay. To control that, the so-called family-wise, they call family-wise error rate, to control for family-wise error rate in some label. Okay, this is kind of divided by m things called bufferonic correction. Oh, for the spheroid, bufferonic correction. Okay, but this kind of correction, it would be very, very conservative. And then, so in the past about 15 years, yeah, since I'm a graduate student, I think. Okay, so a lot of people proposing different adjustments. For example, it's they might put alpha 1, okay, maybe put alpha 1 as really, really small value. So you could imagine that it's as long as alpha 1 is small, right? The error rate 1 minus times 1 minus alpha 1, the alpha 1 contribution is going to be very small, okay? So some people were testing about is give alpha 1s to a really, really small p-values, which means that it's not reject anyway. Okay, imagine the p-value really, really small. Okay, then if you give them still, for example, 10 testings, if you still give them like 0.005, it's kind of waste, isn't it, right? Because p-value is so small, you reject anyway. Why not give that testing a really, really small as well? As a cutoff, alpha 1 is. Okay, then reserve your errors, reserve your family-wise errors to some bigger p-values to see if I can reject it or do not reject it. Okay, so that means in the past 15 years, 20 years, a lot of people proposing this kind of adjustments, right? For example, the most famous one would be Benjamin-Hartberg procedure to do so. Okay, good. I think this is a big field of the multiple testings. I think it's still growing. So if you're interested, you can definitely Google about multiple testings, and then you will see how people do in terms of adjustments of multiple testings. Okay, good. So I'm going to move to the p-value things. Any question about the intersection union or union intersection test? Okay, I don't see anyone have any issues. Okay, so let me move to the statement of p-values from the ASA. Okay, good. So when I'm a part of this, well, I have told you that it's unfrequent test. So the big five of p-values sometimes just annoy me a little bit. Okay, I have to say it. I just see a bunch of patients talking about not using p-value anymore, but really annoy me in somehow. But the whole p-value fight is actually people wrongly using p-value. Again, I said it again. I'm more frequent distribution, but I won't like change p-value that way of like a patient just p-value is. But it's p-value is not only criteria you will make decision. Again, statistics about collecting the data to do inference to make decision. Remember, I said posing any different rejection regions, different rejection rules. Some are good, some are bad. You're using power to compare between them, right? So that means you collect data as a biostatistician, statistician, data scientist. You're proposing your rules to make decision. Okay, p-value is one of them, not every of them. But what we cannot stand is what? Wrongly using p-value. Okay. Okay, good. So read it through. Well, you guys at home, right? Need something to read. This is a good thing to read, I think. Especially article coming from American statisticians is really good articles. Okay. They are not written as technically speaking. They are not written bunch formulas. They are talking about how statistics actually was applied to the life, and then what kind of things is science, what kind of things is not science, something like that. It's really easy to read. Okay, and then I want to point out that the formal statement, a bunch of things right here. Okay, so right here. Okay, so it's follow point by point. I'll give you my opinions. Okay, you don't necessarily believe me or not. I mean, I try my best to give you what I'm thinking, but I'm not necessarily right every time. Right? Good. So remember, p-value is what we say that is after collecting your data. Then you have your distribution of your statistics, and then you should pin down, right? Okay, I'll show you here. It's right. Remember, I say what's p-value? P-value is you do a distribution of your statistics, right? And then t, and then you do have your observed, t observed, right? And then p-value is about how likely your distribution of t as a probability bigger than you observe. This is called p-value. Okay, but again, I said it's p-value is what? P-value is probability given null hypothesis, what the data told you. Okay, good. Okay, so the number one, p-value can indicate how incompatible the data are with a specific statistical model. Basically, I think you can read this through. I think basically told you that we always assuming that it's no hypothesis, it's no association, something like that, right? Or theta equals to 0 or not, something like that. So again, we try our best to reject the null hypothesis. Then p-value basically gives us some evidence to say how your null hypothesis is wrong. But most importantly, this is a really good indication. P-value is not measure the probability that study hypothesis is true, which means that it's p-value. Okay, right here. P-value is not probability of null hypothesis. This is definitely wrong idea. Okay, so you as a statistician about statistician yourself, this is definitely something you cannot say. Okay, p-value is not probability of null hypothesis. Okay, or p-value is not really probability that data were produced by random chance alone. Okay, again, p-value is a probability. You cannot say p-value is not probability. P-value is still probability, but p-value is not probabilities of null hypothesis. Okay, so then scientific conclusion and the business or policy decisions should not be based only on whether p-value pass a stasis threshold. Okay, basically it's in terms of our life, medical journals tend to report it only p-value more than 5%. Okay, such that it create what? Publication bias. Okay, so that means it's also saying something about p-value itself is what? Really, when you do your analysis, I was joking on this, right? So if you see p-value is 0.051, what do you think, right? You will say, well, using 5% rejected, so this is not significant, right? How about p-value is 0.049? Yeah, rejected because of smaller than 5%. And then how far these two guys are? Not much, isn't it, right? So that means don't just using p-value alone, like 5% cutoff. Got to make that decision saying is one rejected, the other one do not reject it. Don't go that fast. Okay. Of course, every statistician have their own way to deal with this. Okay. I'm not going to tell you my way to deal with this. You think about your own way to deal with this. Okay. So basically means that it's, again, p-value is only one of evidence you could make a decision. Okay. So then number 4 is proper inference requires full reporting and the transparency. Of course, nowadays, we want to be our research to be more reproducible. Okay, so it relies on bunch of reporting transparencies. Okay, good. So, and then number 5, a p-value or statistical significance does not measure the size of an effect or the importance of the results. It would do guarantee you in your future career, somebody is going to say something like, hey, p-value smaller than 0.005. It's very significant, right? Okay, then you have to be patient to tell them that it's the value of p-value itself, not necessarily means that they have a bigger size of effects. That is, which basically says that you cannot say smaller p-value is more significant. Okay, good. So then, by itself, a p-value does not provide a good measurement of evidence regarding a model of a hypothesis. So basically together it's, okay. So p-value itself is not really, the value of p-value itself not really give you how strong evidence is. Okay, so again, I'm not necessarily speaking really specifically for each point. I still encourage you guys to read through what each statement would teach you, would learn from it. But most important is, okay, if you say, hey, p-value, you need to be careful. Do I have any options? Of course, again, it's other approaches. Okay, and then the reason I want to talk about this is we are going to talk about so-called confidence interval, which means that it's, if you are not, let me see what confidence interval is. It's included. Okay, prediction interval is Bayesian confidence curvature. I remember we need to reporting confidence interval. Where is that? Okay, I don't see it now, but I do remember about confidence interval. So nowadays, even we write a proposal, the grant, okay, we not only reporting p-value, but also reporting confidence interval as well. Okay, trying to give you people a imagination or give idea about how data look like. Okay, why the confidence interval is going to say, well, you have too much variation, so your evidence is not really strong. Okay, and then I'm going to say about confidence interval, but before say so, I really do want to mention one thing. It's hopefully we are going to cover Bayesian methods. Okay, and but I do want to point out one thing is, if you are choosing the p-value, you are using cut of 5%. Okay, say if some Bayesian told you that it's, why do you want to use 5% to choose a cutoff? Well, you were saying it's, well, it's more probability, right? And then, but don't believe one thing, Bayesian method even using Bayes factor to do the decision making, they still need to choosing some threshold to do the decision then. So don't believe Bayesian saying is choosing 5% is ridiculous. Okay, good. Well, I possibly saying too much. Let's go to our class. Okay. So right here, it's, if you don't like a p-value in some sense, okay, or right nowadays we tend to not only reporting p-value but also report confidence interval as well. Then it relies on so-called interval estimation, which is a topic we are going to cover in this chapter. So what's the motivation then? Okay, the motivation is as such. So say if you x1 to xn, x1 to xn, is no more theta 1. Okay? And then we all know that its probability of x bar equals to theta is 0, because x bar itself is a continuous random variable. The probability of a continuous random variable equals to some fixed point is 0. Okay, so therefore, so even though x bar is a good estimator for theta, and then we do know that x bar is consistent estimator for theta as well, right? X bar is a good estimator of theta, but in the sense of what? It will never equal to theta. Okay, so that means x bar is going to around theta frequently, but x bar is not going to exactly equal theta. That's continuous case. Even by discrete statistics, discrete random variable, what happens? Okay, if x bar follow n theta, okay, theta is some values between 0 and 1. Okay, we all know that x divided by n is MLE of theta, right? You could do the derivation, and you will know that MLE of theta is x divided by n. Okay, so we can actually calculate probability of the MLE exactly equal to theta. Okay, it's not like a continuous random variable. It's discrete random variable. So you might actually have a probability right there. Okay, but it got to be the same as what? Theta got to be one of them. Right? Because x is 0, then 1, then 2, until n. Okay? Of course, I said theta doesn't cover 0, so right here, there's no 0 right here. Okay? There's no 0 right here, because I said theta not going to be 0. So x is 0, doesn't count it here. Okay? So that means in order for that equation to stand, the theta is going to be one of them, 1 over n up to n minus 1 over n. Yeah, there's no 1 right here as well, right? There's no 1 right here as well. Okay, good. And then you can actually calculate probability of x and x divided by n equal to theta. You could do so. You can actually calculate the probability of x divided by n equal to theta. Okay, of course, theta is 1 over n. Okay, so such that it's, you could say theta divided by n equals to I divided by n. So x equals to I. So because x equals to I, x follow binomial, then you can write down binomial's PDF and then calculate the probability of x equals to I. And then when theta is I over n. Okay, but you will find out this probability can be very small, especially for larger n's. For example, if you're choosing n20, theta half, okay, that means right here is probability of what? It's x equals to I, x equals to 20 times n theta. I equals to, let me see if I make it wrong, I make it correct. X equals to I is n theta. Yes, n theta is 20 times f. That means you calculate the probability of x equals to 10. Then by binomial, this probability is going to become 0.18. Will be small. Okay, well, 80% still somehow bigger than 0, right? So 80% not big, but not that small as well. It's fine. But whenever you have in that n up to 100, even though theta still 1/2, then going through that probability is going to become 8%. That means when n is larger, the probability of this guy right here, okay, will become smaller and smaller. Okay, it's not surprising, right? The way I say it's not surprising is what? We all know that it's when n is larger and larger, if when n goes to infinity, then even though your binomial is going to be, even though your binomial is discrete random variable, when n goes to infinity, your discrete binomial distribution is going to behave like what? Behave like normality. It's a continuous random variable x. So it's not really surprising to see when n is bigger, the random variable itself equals to exact number is going to become low and low. Okay. So that means that it's, even we do know that point estimation is going to around your true values with high probabilities, but we still want to have some sense about how likely if my random variables constructed some kind of interval. Okay, that means if I have S bar right here, if I have theta right here, if I do having that in terms of interval sense, I would know that how likely my interval is going to be covered through theta, right? So that means even though point estimation would be close to theta, okay, we still rely on so-called interval estimation to see how good we can do inference on the theta. Or saying that it's, if we do have their high probabilities containing that true parameter theta, we are looking for that. Okay, so that's why interval estimation could give us another set of inference tool to make inference on theta. Okay, good. So, well, in this class, we always change and we always like express all the thinking in terms of mathematical formulas. Okay, so how do we using so interval estimation right here then? Okay, so you do have interval estimation is from one end to the other end. It's a lower bound and upper bound. Okay, because both are inference after collecting the data X. So lower bound or upper bound are both function of the data. Okay, of course, lower bound is going to be smaller than upper bound. That's trivial. Okay, so you could denote it by either its parentheses or bracket, either way. Okay, yeah, of course, if your X is really discrete, then parentheses and then bracket will make difference. If the X is continuous variable, then these two guys don't make any differences because we do know, at some point, single points probability is 0. So either parentheses or bracket will be fine. Of course, you have one-sided, saying that you have up to some value right here, A or B right here, okay, or A up to some value right here. You might have your lower bound or upper bound opened up to infinity, then that makes it a one-sided interval. Then the next one is coverage probability. Coverage probability a little bit confusing. The way I say it confusing is this. So if theta actually fixed at some point, okay, then it's not confusing anymore. Okay, you would think about it. We don't know my lower bound, how likely my lower bound and upper bound is going to cover that theta in a probability sense. Okay, that's so-called coverage probability. But in some situation, your theta actually moving, not a fixed point. then at that point, we are going to do so-called implement of the coverage probability right here. If theta do have many points in the kernel stage, then you might want to figure out what's the smallest value of coverage probabilities to make that so-called confidence label. Okay, so this really some terms we learn a lot, like what 95% confidence interval. That actually means as confidence label right here. Okay, again, if theta actually fixed, then 95% making sense. But if your theta actually moving, you might want to know which theta actually give you smallest coverage probabilities that become confidence label. This is example. Okay, so if X is Bernoulli theta, again theta right here has many points, right? From 0 to 1. From 0 to 1. Oops. From 0 to 1. There are many points in theta. So that means you have to talk about where the theta is, okay, to get that probability of the interval. I'll cover it, okay. For example, right here, if I do have a confidence label like this, from 0.4 to 4, from 0.4 to 0.5 to from 0.4 to 0.5, but plus what you observe. If X is 0, then it's from 0.4 to 0.5, right? If X 0, then the interval is from 0.4 to 0.5. Okay, then if X1, then it's from 0.4 to 0.7. Okay, good. Then the definition of coverage probability is the probability of theta belongs to that interval. So that means CP theta equals to probability of theta. Lower bound will be 0.4 minus 2 theta, 0.5 plus 2x. Okay? So say, right here, your interval either this one or this one. Your interval either 0.4 to 0.5, or you're either 0.4, 0.7, depending on what observation of X is. Okay. So if your true theta is from 0 to 0.4, look at these two intervals. Does that cover theta? No. That means when theta from 0.4 to 0.5, these two intervals not going to cover theta. Okay, so that means the coverage probability is 0. Okay, of course this guy is smaller than, so not equal to, not is smaller than, so not cover 0.4. So this is, although I write bracket right here, so this should be fine. Okay, then what if theta is actually 0.4 to 0.5? Okay, why this guy 1? That guy 1 is, even though no matter what value of theta is below, no matter what value of theta from 0.4 to 0.5 is, these two guys all cover 2 theta. Making sense? Okay, good. So then using the same logic, right? What happened here? If the theta is from 0.5 to 0.7, okay, then which one actually covered? Okay, look at these two guys right here. Look at these two guys right here. If my true theta actually 0.5 to 0.7, does this guy cover? No, right? this interval only happens, this interval only from 0.4 to 0.5. It won't cover theta, but this guy does cover theta. Okay, then how likely you have interval like this? That likelihood, that probability will be what? Only happens to probability x equals to 1, right? As long as x equals to 1, you have the interval, then you cover true theta. Then that means the probability of the interval cover theta is probability x equals 1 by Bernoulli is theta. That's where this theta comes from. Okay, then again, it's if theta bigger than 7, smaller than 1, looking at these intervals, looking at this interval, looking at these two intervals, what happens? If theta actually bigger than 7, both are not going to cover true theta. So the coverage probability is 0. Okay, good. And then going back to say, what is the confidence coefficient? It's increment of your coverage probabilities on different value of the theta. Yes. Then look at this. Look at this. Where does the increment occurs? 0. The lowest value of the coverage probabilities over the theta, over the perimeter space theta of theta is 0. So you do have 0 confidence of this interval going to cover the true theta. Okay, good. So I hope you guys gradually having that sense about confidence interval. Okay. Any questions right now? Okay, so far so good. So I'm going to go even deeper. Okay, how do we define a confidence interval then? Okay, method number 1, inverting a text. Okay, so because we teach about hypothesis testing, so you're able to say, assuming null hypothesis theta equals theta 0 versus alternative theta doesn't equal to theta 0. If I give you that, then you should be able to construct a level alpha test, right? Okay. So number 1, how do we find confidence interval? Number 1 is inverting the acceptance region of a level alpha test. Okay, good. So right here is exactly the acceptance region is, because I say delta is decision rule. Okay, delta is 1 rejected, delta is 0 not rejected, acceptance, right? But its acceptance region is delta equals to 0. Okay, so it's still function of x. Let me told you, this is notation of Kassenberger. I don't like it, but I have to use it because I think the right-hand side is really not the function of x, but that's how Kassenberger denote it. Let's use it. Okay, by any means, it's converting a assembly region to inverting the assembly region to the confidence interval is actually very, very easy. As long as you do know how to construct it, the assembly region, then really look at your region. You take out thetas. You take out theta 0. You just bring your eraser, right? You take everything. You write your theta 0 to become theta. You got it. Okay. So here's an example. What I mean by you just bring your erasers to take out every theta 0, then become theta. Okay, you erase the zeros into a separate region. Okay, so we do have a theory right here. I'm not going to go through the detail right here. Okay, which means that it guarantees that when you do your inverting from a several regions, they will give you your coverage probabilities bigger equals to 1 minus alpha x. Okay, of course, if you do inf right here, become like confidence level, right, among thetas. Then smallest one would be what? 1 minus alpha. That's the reason why we can call it 1 minus alpha constant interval, because the minimum value of that probability is 1 minus alpha. So we can call it 1 minus alpha confidence interval of theta. Okay, here comes example. Okay, so so x is a random variable, size n. Okay, size n right here from normal theta 1. Okay, if you do testing, theta equals theta 0, then theta doesn't equal theta 0. Okay, say if I do LRT right here. Oh, any testing making sense? Okay, good. So if you do LRT right here, more than likely you will find what? Two-tail rejection, right? Because single points versus composite two tails, right? We talk about this guy. Well, just reminding you, it's this guy doesn't have ABOP test, but that two-sided test is very powerful. Okay, so right here is what you would find. This test region is actually based on LRT. Okay, but it also could be really trivial about saying this test making sense. Okay, say, well, okay, hopefully I don't confuse you. Okay, I still want you to working from LRT first, and then find these test regions. Okay, good. Say if you find test regions right here. Okay, so how do I invert my test region to become constant interval then, right? Again, it's what? This is how you write your acceptable region X, right? This is, so you more than likely is alpha equals to, I rejected x bar minus theta 0. Then this guy right here bigger than 1.96, or x bar smaller than x bar minus theta. X bar minus theta 0 divided by 1 minus over n smaller than 1.96. Right here. This guy is theta 0. Okay, then actually it's not only about alpha, but also actually it's what? 0.5. Okay, so you'll write your rejection region like that way, isn't it, right? Either this guy too big or this guy too small, right? Smaller than cutoff, something like this. You do have this guy normal 0.1, 1.96, minus 1.96, right hand side 0.025%, left hand side 0.025%. Then such that your alpha is 5%. Okay, so that's your rejection region, and then you just using that the rest of regions to become acceptance region, right? Sorry. Okay. So it's a complement of a region. You just write it that as a accepted region right here. Your theta 0 is between x bar minus, so it's right here, right? Right here. Okay. So you're working on the formula right here. You find out one side that is this guy. Okay. That means your theta is between theta 0 is between your 2 points A and B. You're putting 2 points right here, become a same region. Okay. That means how do I find constant interval then? Again, I said it's just bring your erasers. Take theta 0, take theta out, then become your constant interval. That's it. And they guarantee that this guy is 95%. That's way by the theory. Okay, that's how easy that is. Inverting a constant interval inverting a separate regions to become constant interval. Okay, good. Another example would be this right here. Okay, you do have x1 to xn exponential theta. Okay, I don't know if you remember this, right? So I do give that as a midterm number 2, right? I think so. T1 to Tn exponential theta. Yeah, this is midterm number 2. Okay, so then you do have null hypothesis theta 0, alternative theta doesn't equal theta 0. Okay, then by LRT, okay, I'm not going to write in detail, pardon me on that. So let me check out your midterm number 2. I haven't graded yet, but let me check out how many of you actually don't get it. How to derive LRT? I want to know. But I suppose you guys are working from home, so you guys should have a bunch of opportunities to look at how to construct that laboratory test, and then eventually get these kind of things right here. Okay, this is nothing but lambda x bigger than c. This is nothing but lambda x. Okay, so say if you're struggling to find this lambda x, don't hesitate to let me know. I can derive in that for you on my end. You will see that really based on principle, okay? And then you will get that lambda x. Good. Again, it's what I say is what? What I say is, how do I convert it? Oh, sorry. So of course I said it wrong. This is rejection region, lambda x smaller than c. If I say that's pardon me on that, let me make it clear. So we all know that the rejection region of LRT is lambda x smaller than c. Okay, that's rejection region. And then the acceptance region denoted by a theta 0 is bigger than c. Okay, that's exactly right here, bigger than c. A separate region. Okay, and then how do we invert the acceptance region to get a 1 minus alpha confidence interval then? I do have my erasers. I will just erase all those nuts. Erase. Then I got it right here. Okay, then you got your 1 minus alpha comes interval bigger than c. Okay, so let me tell you something. You might not necessarily understand it. It's okay you don't understand it, but it's always good to learn. Okay, let me ask you one thing. By saying so, I basically told you that it's probability alpha 1 minus alpha equals to probability theta. Then summation xi theta n exponential minus I from 1 to n. Pardon me, spend time to write this. See. Okay. If I say so, hey, this is the confidence interval of theta. Did you actually show interval here? Do I actually write something like a previous example? It's what? Lower bound, theta, and then upper bound. Do I write that? I don't. Then, could I say this guy still 1 minus alpha comes interval? Yes. But the point is, if you do want to say this guy right here, much easier for people to understand. Then how to get it? How do I knowing about this guy and then convert it to me this guy giving specifically about theta, bigger or smaller than some lower bound and upper bound. Okay, how do we do it? You can double check CMB, Katzenberger to help to find it. But let me tell you, it's not really difficult in terms of nowadays. Okay, so this guy right here means what? This guy in the right hand side here means you basically finding any theta from lower bound to upper bound that satisfy this inequality. Making sense? C right here is constant. You know that somehow. Okay? You know that somehow. And then this is a whole inequality, especially if you remember I emitter number 2 is I say the left hand side of this function right here is what? Is a quadratic function or concave function of summation xi. It's actually also concave function of theta. Actually. Okay? So, oh no, it's not concave function of theta, right? If I bigger than C, oh yes, concave function, yes, concave function about that theta. The left-hand side inequality here means what? That means I'm looking for anything bigger than C right here. Okay, let me draw a better graph. Sorry about it. Means this guy right here, theta. Okay, function of theta right here. This guy concave function of theta. And you're looking for C, cut of C right here. Cut of C right here. Okay. And I'm looking for bigger than C. Bigger than C. That means mapping to the theta is these 2 points. This is your lower bound. This is your upper bound. Okay. Is that doable? Yes. Is that easy? Not necessary. Because you might need to some skills about numerical analysis, trying to find which lower bound and upper bound belong within that 2 bounds. Their function satisfy function of theta equal to C. Okay. So if you don't know what I'm saying, it's totally fine. But I just want to point out it's even though sometimes we'll write something right here, not necessarily interval sense, but actually that could be easily converted to an interval, like we always saw, theta bigger than lower bound and smaller than upper bound. Okay, then 7 minutes left. So let me go through other things about sometimes you have something like what? I also can convert. So imagine that it's in order to find constant interval, if you told me that it's I can invert a separate region to become a constant interval, right? But I did not say you have to look for some specific testing. Okay, by that two-sided test, that give you something lower bound, upper bound right here. But it also stands for if I actually testing about simple versus composite and then one-sided and then inverted, that one's still valid. Okay, again, it's inverting a separate region, not necessarily inverting two-sided test. I can also inverting one-sided test. Okay, but in that case, you will find out it's you actually having this one-sided interval as well. By doing that, you will find lower bound and your upper bound is open. By doing so, you find upper bound, but your lower bound is open. Okay. That also tells you what it also tells you one thing is what your constant interval, your 1 minus alpha confidence interval is not unique. You could use in this guy right here, have lower bound, have upper bound. You could use this guy right here, only have a lower bound, upper bound open. You can use this guy right here, have upper bound, is lower bound open. 3 of them all have that 1 minus alpha confidence interval, or all of them having that 1 minus alpha confidence. Okay? So, example is here. So, x1 to xn, again, theta sigma squared. Okay? But right now is I think I purposely saying that is sigma squared is not known. Sigma squared is unknown, I think. Otherwise, you might not necessarily using this guy t-test right here to do testing. Okay? If sigma squared is known, you were using the way we showed before, the z-test is. Okay, good. So I think right here, sigma squared unknown, so you're using t-test to do rejection. Okay, and then for that, I think you can basically construct it. I think doing which test? This guy, right? This guy, right? I may be wrong. By any means, it's you. One of them, you have that one of them, you have that acceptance region. Look at this way. Look at this way right here. Okay. Again, how to invert? Again, bring up your eraser, taking out theta. Okay. And then working on little algebras to get this. Okay. Then that becomes theta smaller than x bar minus in the left hand side right here. Okay, so that means this guy is what? This guy do have an upper bound, do have a smaller length. So you do have upper bound. This is upper bound right here. You do have your upper bound, and then your lower bound is minus infinity. Okay, then inside guy right here is 95% confidence interval of theta. Okay, good. So that means don't forget about your eraser. Good. Okay, so I think I've covered everything I'll cover for today. And then let me summarize a little bit, 2 minutes left. Okay, so in this chapter, we are learning about how to find confidence interval. Okay, the first way you use, or the first way to find it is actually inverting and means that it's not only unique, the inverting and accepted region of a test, then to become confidence interval. Okay, but imagine if you do that, it's actually a long route, isn't it? Right? So you need deriving the test, and then you imagine how much time you spend for LRT, right? And then you deriving so much LRT, then you take your eraser, then you find the intervals. It's taking a long time. I have to guarantee you. Okay. Then instead, in the next week, we are talking about another way to find confidence interval, which is much easier, and then which is much straightforward. Okay, it's so-called pivot or pivotal quantity to find confidence interval. Okay, so what does that mean by pivotal quantity then? Pivotal quantity is a pivot, is a statistic actually function of x. Okay, but its distribution is independent of theta. Okay, you will see how easy that is using that pivotal quantity. Okay, then straightforward to say it. Okay, let me use the final minutes to tell you what is that easy. So if you do have pivotal quantity right here, okay, it's a function of data, okay, also function of x as well. If the distribution independent of theta, that means you can easy to write it. I can write A and B right here, pretty straightforwardly. And then because this guy right here, independent of theta, I can pin down A and B easily. And then this guy right here, also easy for you to operate. Eventually you find, write it down as lower bound and upper bound edge. Very straightforward. Because this guy ultimately is our goal. And we are using this guy right here to help us to find what is A and then what is B. Then just do little algebra. You can pin down theta in the middle and then find lower bound and upper bound. Okay, good. Okay, it's 1:45 right now. I'm going to stop here. Any questions?
Yeah. Can I have a question?
Yes.
About lower confidence bounds and the upper confidence bound on slide 10.
10 right here.
Yeah. So for the lower confidence bounds, the H1 is 0. Well,
Okay.
it gives the interval. Well, it gives the lower confidence bounds. But I thought that the confidence interval is more related to the acceptance region.
Yes.
Than the,
and then.
So I thought maybe the H greater than 60 will give the upper confidence bounds instead of the lower confidence bounds.
We can double check an example right here. So look at example right here. Okay, let me stop recording. So I don't think everyone have to